share my screen. Yes. Share screen. Sheesh.
Wait, Mr. Cameron, you use Zoom on your
Mhm.
iPad or on your laptop?
Oh, I do it on both.
On both?
Yeah, so I'm like hosting the whole meeting on my laptop while I connect my iPad so that I can share the screen and do all that, extra drawing and stuff.
Oh, yeah. All right. Yeah, I don't know why that was happening with the Zoom thing.
Yeah, me neither, but I'm gonna fix it soon.
Yeah, all right. I thought you weren't there, and I was like, all right.
No, I was there. It just wasn't popping up for some reason. I'm like, why is it not popping up? And it's sending me emails, but I can't see it in the actual Zoom. Like, what's happening? No, this is the wrong. All right. So this is the 2018 exam 2 practice exam. So let's get to it. So it's like this. All right. Question 1. Which of the following statements about electronegativity and the periodic table is true? So first one says electronegativity decreases left to right across the row of the periodic table. Is that true?
Nah, it gets bigger left to right.
Right, exactly. As you go left to right, so let's like do this. You have hydrogen, you have boron, carbon, nitrogen, oxygen. As you go left to right on the periodic table, electronegativity increases, not decreases. So 1 is incorrect. So which of these answer choices match what we just said?
That's a C, the third one.
Third bullet point, electronegativity increases left to right, always. All right, question 2. Identify a Bronsted-Lowry base. So acid, not base. So in other words, he also says Bronsted acid instead of including Larry, right? Lowry. So what is a Bronsted acid?
Bronsted acid. I'm pretty sure the was it? The Lewis is like the opposite from the Bronsted. Because I asked the
Yes, it's
professor.
it is the opposite.
Yeah, that's how I'm gonna remember it. I'm pretty sure the acids what, and the Lewis, the base gives like the electron to the acid, so the acid gives the proton to the base.
Right. Bronsted acids are species that donate protons. So which answer choice best matches what a Bronsted acid is?
It's gonna be B.
Right, the second one, a proton donor. So remember, the definitions for the Bronsteds and the Lewises, they are pretty different, but they still like relate to one another. Bronsted acids is a species that donate protons. A Bronsted base is a species that accept protons. So with Bronsted, it's more related with the hydrogen atom, where it's going to be donated to and who's going to snatch it. The definitions for the Lewis base and acids, they're more towards the electrons because the Lewis base is an electron donor and a Lewis acid is an electron pair acceptor.
Okay.
Right. So
Yeah.
Bronsted is more electrons, Lewis is about the electrons.
All right.
3 is kind of faded out, but we already kind of worked on questions like this. This is an acid-based question, so we could definitely do this one. So you can see it.
Yeah, yeah.
It says, which of the following compounds is not a Lewis acid? So again, what is a Lewis acid?
Lewis acid is it's the acceptor of electrons.
Right. It is the species that accept electron pairs. So it accepts the electrons that are being donated to it. So we have like 4 compounds here. We have BH3, AlCl3, CH3, CH3, and CH3, CH2 plus. So CH3 is like this. Would this be a Lewis acid?
No. No.
Remember, yes. The boron is a Lewis acid because they can accept electron pairs. So they can accept the pair so they can complete their octet. And boron works the same as aluminum here. The AlCl3 is the same thing. It only has 3 bonds now, but it can still accept an electron pair to complete its octet.
Okay.
CH3, CH3, that's, write it like this. 3HC, that's the CH3. And then the last one, CH3, CH2 plus. So let's spread that out. It's like H, and then a positive charge. So out of the 2 species here, the CH3, CH3, and the CH3, CH2 plus, which do you know is definitely a Lewis acid?
Lewis acid meaning it accepts
Mhm.
electrons. So I assume I assume the one with the positive charge.
Right, because we see that the carbon is electron deficient, which is what that positive charge is telling us. So the only species out of all 4 of these molecules here that cannot accept electron pairs is these 2 methyls attached to each other, because the carbon already have all 4 bonds. It's not electron deficient, and it's not electron rich, it's stable. It's just, it has all 4 bonds to maintain its stability. So the answer is 2 methyls. CH3, CH3 cannot be a Lewis base. I mean acid. Keep saying this.
Because it has like all its bonds.
Right, it has all its bonds. Carbon has all 4 bonds that it needs, and it's not electron deficient.
And then can you explain the 4th answer again?
Oh, this one?
Yeah.
So this species is a Lewis acid because the carbon here has a positive charge, which means that it's missing electron pairs. So it's very electron deficient. So a pair of electrons can be donated right into that carbon cation spot.
Okay.
It's looking
Cation
for those electrons.
cation meaning positive charge, right?
Right. No,
Okay.
sorry, not cation. Carbocation is positive charge. There we go.
Okay. All right.
Any other questions about 3?
No. No, not
Alright,
really.
so let's go to 4. Which of the following molecules is most likely to act as a Bronsted base? So, what is a Bronsted?
Bronsted base. Um, it receives protons. Does it? Hold on.
Right.
Yeah, it receives protons.
So, Bronsted bases are species that accept the protons that are donated, right?
Yep.
So in order for them to accept the protons, what do they have to have on that species?
I have no clue, actually.
So you need lone pairs. Remember, a base, in order for them to accept not the electrons, in order for them to accept the protons, they have to have electron pairs to donate to the proton to accept, because it snatches it off. Remember, it's a homolytic cleavage from the proton on the acid. So the base has to donate an electron pair to the proton so that it can keep the proton to itself and then both the electrons from that, whatever bond the acid had, like let's say OH, both of it will go to the O. So you need electron pairs. So the CH3, all 4 bonds in that carbon already, so there will be no lone pairs on none of those carbons.
Okay.
The second species have fluorine. You do have 3 sets of lone pairs around the fluorine, right there. Third species, you have an oxygen, only 2 bonds directly to that oxygen, so you know it's 2 pairs of electron non-bonding there. Same thing for the fourth species here. 2 non-bonding electron pairs on that oxygen. And in the last species, this nitrogen has 3 physical bonds around it. So only 1 set of electron lone pairs on the nitrogen. Now, you see these electrons, right? So in order to figure out which one will react with the proton, what do you think we have to look at now?
What do we have to look at now? The species that accepts the proton?
Yeah, you have all these non-bonding pairs.
Yeah.
So now, what do you think we have to pay attention to figure out which of these non-bonding pairs is going to react with the proton?
Their electronegativity? I have no clue.
So electronegativity would play a part, yes. So you do look at the electronegativity because non-bonding lone pairs on the most electronegative atom, you already know is not going to be very reactive. Because let's say, for instance, oxygen is very electronegative. So those lone pairs are not as reactive. So we do look at electronegativity, but the one thing you should pay attention to is the bonding electron energies. So which of these non-bonding lone pairs are higher in energy? The ones that are highest in energy will always be the ones that would react first with anything. So that would react with a proton. So you have non-bonded pairs on a fluorine, 2 sets on these 2 oxygens here, and 1 on a nitrogen. Which of these non-bonded lone pairs do you know is very reactive?
Do I know is very reactive? Very reactive. Is it fluorine?
Remember, fluorine is very electronegative. So those lone pairs aren't going to react as much. Which of these atom species do you know is least electronegative with the non-bonding lone pairs?
It'd be nitrogen.
Right. So since nitrogen is in the far left side, not far left, like further left than oxygen and fluorine is least electronegative. So those non-bonding lone pairs will react with the proton because it's more reactive.
So more reactive is more electronegativity?
No. A more reactive pair of electrons will always be on the least electronegative atom. Because electronegativity is what helps stabilize the electron energy of those non-bonding lone pairs. So like these non-bonding lone pairs of fluorine is way more stable, they're least reactive than the oxygen ones, but oxygen is still more electronegative than nitrogen. So the only non-bonding lone pairs that are very reactive right now are the ones on nitrogen here.
Okay. All right, wait, so I'll just remember it like this, all right? You said less electronegativity means more reactive. Essentially, okay.
Right. Non-bonding lone pairs on a less electronegative atom means that it is very reactive. So those would be put into those electrons there would snatch the proton.
Okay. All right. It's a little bit better.
Mhm.
All right.
Go to the next section. I'm sorry, hold on.
That's all good. I'm gonna get water.
All right.
I'll be right back. All right.
So 5. This is another question. It's another type of acid base. Gotcha.
Yep.
So which of the following bonds is the strongest and most acidic? So you have a CH bond, an FH bond, an OH bond, and an NH bond. So let's look at it like this. Have hydrogen, then oxygen. Boom. So as you go left to right on the periodic table, what happens to bond strength? You remember that periodic chart?
On strength. Off the top of my head, bond strength. It decreases, right?
It increases.
Okay.
Remember, bond strength increases left to right on the periodic table because the atoms further up, they're becoming more electronegative, right? So the electronegativity is what's helping. It's what's helping to keep that bond between whatever that atom to another atom is, like for example, these OHs and FH and stuff. So the more
Yeah.
electronegative the atom is, the more bond strength you would have with the hydrogen. So it increases as you go left to right. So
Okay.
bond strength increases left to right. And let's remember, we just learned about the acidity trend, right? So acidity, as you go left to right on the periodic table, what does it do? Increase or decrease?
Oh shoot. Okay. Acidity.
Mhm.
What does acidity do? Okay. Um, let me think. Hold on. 5. Wait, what am I? What would acidity do? Would it decrease?
It would increase.
Oh,
Think of it like this. Acidity follows the same periodic trends as electronegativity.
okay.
So as you go from left to right on the periodic table, electronegativity increases, bond strength definitely increases, and acidity. So it makes sense that the strongest bonds, the more electronegative atom, would be the most acidic as well. So you have carbon hydrogen, fluorine hydrogen, oxygen hydrogen, and nitrogen hydrogen here, bonds here. Which of these bonds would be the strongest?
It'd just be the fluorine one, right?
Right. The fluorine hydrogen bond is the strongest. And because it's more electronegative and acidity follows the same trend as that, it would also be the most acidic molecule.
Okay. And then as like for the periodic table, when it goes like up and down, it's like the more up the more up like the elements are on the table, it's like the more acidity and
Right.
stronger they are.
So remember, as you go from bottom to top, acidity also increases that way. Acidity increases bottom to top.
All right.
Going from top to bottom, obviously basicity increases from top to bottom.
Okay. And just to make sure, right? The lecture tomorrow, is it going to be on like stuff that's for the exam?
So what happens is before Ben goes into new topics, he might just go over like he might do a summary recap of what you guys learned so far with the reactions. So like the
Okay.
acid and base. Also remember that you will have your, I believe, addition. Is it addition? Maybe not addition. Maybe like 2 on addition. Well, you learned addition and you learned a substitution as well.
Yeah.
So he would do a recap on what you guys learned so far, and then he would still move on with the lecture. But he will. Oh, it stops after acids and bases. Like everything you've learned from the beginning to acids and bases is what's going to be in the exam.
Okay. All right.
Yeah, he might touch up on it. He might. But just for a little bit, because they gotta keep with a schedule.
Yeah, yeah. That makes sense.
All right. So 6. Which of the following species is the least stable? So you have OH minus, which is obviously this. OH. This is hydroxide. Water, H2O. Have your oxygen, 2 lone pairs attached to 2 pipes. That's H2O. O2 minus is oxygen by itself with all these lone pairs. So this is O2 minus.
Yep.
And hydronium, which is this HDO plus, is the oxygen with 3 bonds and a missing set of lone pairs. So you have all 4 of these species here. And the question is asking which of the following species is least stable? Which is stable. So when you're answering this question, you want to ask yourself, the main purpose of chemistry is to do what to what?
Is to do the main point of chemistry is to do what to what?
So what are we essentially doing at the end? In every chemistry thing we've learned, we're doing what?
Um like answering questions on an exam, or you mean like writing
No, I
down?
mean like in chemistry, we're learning all these new things, right?
Yep.
Essentially, what are we always doing in chemistry? The main thing.
What are we always doing?
Mhm.
Learning about new compounds.
Yeah.
The question's weird what you asked. What are we doing? I mean, we're
Yeah. So
applying these formulas to real life, these compounds and stuff.
so in the end,
Yep.
everything we learn, all these new reactions, what reacts with what, we are always creating molecules. We're putting electrons into bonds. That is the main point of chemistry. The number one thing Ben always stresses because when we put molecules, like these non-bonding pairs of electrons that these molecules have, into bonds with other atoms, we lower their electron energy, which makes them stable. So you want to get as much non-bonded lone pairs as you can into bonds so that they could become stable, correct? So we have all these species here. You have the hydronium, the water, the O2 minus, and the the first one's hydroxide, my bad. Hydroxide, water, O2 minus, and hydronium. Have all of these. Now, if our main purpose is to get non-bonded lone pairs into bonds so that they can become stable, which of these species do you know is definitely not stable right now?
The one without the
Mhm.
lone pairs?
Right? The one without bonds at all.
Okay.
Elements that are just floating around with all those non-bonding lone pairs around them, they're very reactive right now because they want to get into bonds. They want to form a bond with some other element so that they can start lowering their electron energies. So that means that this O2 here, O2
Yeah.
minus, is very unstable. This oxygen has no bonds at all. You would have thought that maybe the hydronium wasn't too stable because we do see a positive charge in that oxygen, which of course we know is like, unlikely. It's weird. Oxygen shouldn't have a positive charge, but you do have 3 bonded hydrogens to that oxygen. So you still have the non-bonded lone pairs in bonds to make them pretty stable. The only molecule here that
Yeah.
doesn't have no bonds at all is this O2 minus. So right now, this is very reactive, which is very unstable. It wants to form some type of bond, even if it's just one. Let's get into a bond so I can start lowering my electron energy.
Okay, so you're saying at least if it's stable, it has bonds. More stable means having bonds with other
Right.
elements.
In chemistry, when we put non-bonding electron pairs into bonds, we're starting to make them stable. We're lowering their electron energy. In some cases, of course, when we put it in bonds, you can still say like, it's kind of unstable and stuff, depending on how the bonding is. But in this case, we do see an element here without any bonds at all, which is this O2 minus. So we know
Yep.
that is very unstable.
Okay.
No bonds at all. Its electron energy is very, and it's a -2 charge. It's not even a -1 charge. It's -2. It's very reactive.
If it was a -1 charge, it'd still be the least stable, right? Out of all these?
Well, in order for oxygen to have a -1 charge, it's like this. You see this OH here? It has to
Oh
have
yeah.
one bond to it. So that's the only way it can have a -1 charge.
Okay.
In this case, when it has no bonds at all and all these electron lone pairs, it has to be -2 if you do the formal charge formula, the
Yeah.
valence minus the ohms. So right now it owns 8 and its valence is 6. So that's a -2 charge.
Okay. But the next like least stable compound out of all these is answer A, right?
So
Oh.
I would say next least stable, I would say yes. Because we did learn in acid and base that OH, so, well, you will start learning, I don't think you learned that yet, that OH is a very bad leak. So yeah, A would be least stable too,
Okay.
negatively charged.
All right.
Question 7. A 120 clockwise rotation about the central CC bond of butane will convert the lowest energy staggered conformation into which form? So you're taking butane, so you're taking butane, 1, 2, 3,
Yep.
4. First, we're going to draw its lowest energy conformation in a new projection. So they're looking down the central bond. So like these 2 carbons here. This is what we're looking down.
Okay.
So you draw the Newman with this one. You have your methyl, 1 methyl pointing up, 2 hydrogens. Your back carbon. In order for it to be lowest, you have to put the other methyl anti to it. This is your lowest staggered energy conformation, which is called the staggered anti.
How do you know it's anti again?
Because the 2 big groups, they're facing opposite each other. So like how 1 methyl here is facing up and the other one is facing down, this is called anti.
Okay.
It's another way of saying trans.
Yeah, is what I was thinking. And if
Yeah.
they're on the same side, like the cis thing, it's gauche, right?
Right.
Okay.
All right. So now you're going to take this and you're going to do a 120 rotation. We're going to rotate the big carbon in the back. So the front will still look the same. So let's rotate the back like this. Big carbon, 120 degrees. So the front is still the same, but now the back carbon has been rotated. If you take it and rotate it 120 degrees like this now, what changes? Where's everything now?
Where's everything now?
Yeah, so you're rotating the big carbon in the back, right? The
Yeah.
methyl is no longer anti since you did that 120 rotation. And of course, all these hydrogens would pop up in a different direction too.
Yeah. So it'd
So,
go left.
right. So what happens is you're going to turn it left. The methyl would be closer to this one up here. You have one hydrogen there,
Yeah.
and then the other one, oops, I put an X down here like that. So now you
Okay.
have this staggered conformation. Now, what's this conformation called? Staggered what?
It's gauche.
Yeah, it's the gauche. Whenever the big groups are together like this, close to one another, still 120 degrees apart, that's staggered gauche.
All right. Why'd you rotate that carbon, the bottom one, instead of the top one?
So in most cases, when you're doing a rotation with the Newman projections, they
Yeah.
would always most likely rotate the big carbon in the back. They'll always rotate that one. So they'll keep the front one the same and rotate the back carbon.
Okay. Oh,
Because
yeah.
it's more easier to see versus the front because, you know, the carbon is represented by like this small dot. So with the big carbon represented by a huge circle, it's easier to see the rotation.
Okay.
So that's the answer to 7 for you. Rotated 120 and converted it into a staggered gauge conformation.
All right.
Any questions?
Not at all.
All right. So let's go to 8. In the following compounds, how many hydrogens atoms occupy axial positions? So axial positions is what? Where are they going to point?
Same direction of the carbon they attach.
Right. So they're going to go straight up. Carbons that go up for hydrogens in the axial position, they're going to go up. And the carbons that are pointed straight down, the hydrogens in the axial will go down axial. So where are these carbons? Does this carbon have an axial hydrogen?
Yes.
Right. Up or down?
Down.
Right, because we see our carbon pointed down. So you'll have a down axial hydrogen there. What about this carbon? Any hydrogens?
Yes.
Yeah.
And up hydrogen.
Right, up. You see a carbon going up. For this one over here, we see it going down. So we do have down hydrogen. This one here, up hydrogen like that. Do we have any hydrogens on this carbon?
No.
No. You see all 4 bonds to everything else other than a hydrogen. So we can't put a hydrogen on there. What about this carbon?
Yeah. There should be a hydrogen.
You only
up
see
there,
3
though.
bonds. And that carbon is going down. So we will have a down axial hydrogen. Up for this one, you can see it. Down for this one. Down for the other one. And this, none, because we see 4 bonds there already. So now, I'm supposed to draw an H, I don't know where that arrow came. So now, how many axial hydrogens have we added to this chair conformation?
You have 8.
Right, 8. Yes.
Quick question, right? So picture like the hydrogen that you drew at the bottom left. Shouldn't there be a second hydrogen? So I guess since you didn't draw the other one, it's equatorial then?
Yes. So remember, when it comes to the chair conformations, you
Yeah,
still do have your your 2 hydrogens for the carbons that you only see 2 physical bonds. But remember, the both hydrogens would never occupy the same position because we want it as stable as possible. So that means for chair conformations, we um that's why when we do the Newmans, we have the definitions like gauche and anti. So when it comes to the chair, all the carbons and hydrogens and stuff here, they'll be staggered.
yeah,
And you have like the down ups, and for the hydrogens, you'll have an axial, 6 axial hydrogens and 6 equatorial. So they can be as far apart as possible to cause less steric hindrance.
okay.
So just remember there are hydrogens there in an equatorial position as well.
All right.
Let's go to the next question. Question 9. What is the relationship between these 2 molecules? So you have 2 Newman projections. Is it easy to tell the relationship between these 2 just by looking at it?
They're both staggered, pretty
Right.
sure.
Both staggered, yes. But in order to tell like if they're constitutional isomers, stereoisomers, same molecule or different, can we just say
No.
yes or no? No, it's not really easy. Like some students have that talent, yes. But let's face it, just by looking at it, sometimes you're like, oh snap, okay, I don't know if they're the same, different, or what. So what we can do is try and draw out the molecule and name them. This way we can tell if they're constitutional isomers, stereoisomers, the same or different. So one thing Ben did say is you could do like a sawhorse drawing. So the front carbon, let's represent that by that red dot. And the back carbon, which is the big one, let's represent it by the blue dot. You can draw the molecules. You know what? We just draw the big carbon. Draw it almost as if you're looking at it from a sideways view. It's the sawhorse, like Ben said. So the front carbon, you have this isopropyl joint with your methyl and your hydrogen. In the back carbon, we just have all hydrogens. Right? So this is our molecule we're looking at for the first Newman projection. Now let's name it. What's the first thing you must always do when it comes to naming?
Find the longest chain. Carbon.
Right, longest carbon chain. So how many carbons make up the longest chain?
3, 4.
1, 2, 3, 4. This big carbon here, that's 4.
Yep.
And you have substituent. You have a substituent here, methyl substituent here. So now we got a number, right? Where would we start numbering from?
Top.
Yeah.
Right, the top, because that's where we come into contact with our first substituent. So this is carbon 1, 2, 3, then 4. All right. So now we got all the information we need to name it. So you have 2 methyls, one on carbon 2, one on carbon 3. So how is the naming? What do we say?
2 to 3 dimethyl butane.
Right, dimethyl butane. This is the name of our first molecule. All right, so now the same thing we did for this first Newman projection, let's do it for the second. First carbon represented by the red dot, second represented by the big carbon. Put it together. The first carbon, we have a hydrogen facing up and 2 methyls going off on the side. So I'm gonna draw it the same way, just like that. Second one, have 2 methyls up and a hydrogen facing down, just like that. All right, so now let's get to naming. First thing, longest carbon chain. How many carbons make up that chain?
It's 4.
Yeah, 4 again. 2, 3, 4.
Yep.
Then we have substituents. Boom. Boom. So now let's get to numbering. Does it matter which side we number from in this case?
No, it does not.
No, because either way you start, you'll get to a methyl and a second carbon. So let's start it from the right this time. So 1, 2, 3, 4. Now let's get to naming. We have a methyl on 2, methyl on 3. So what would the name be?
It's gonna be 2, 3, and it's gonna be dimethyl, and then butane.
Right. So for both lumens, we get 2,3-dimethylbutane. So what's the relationship between the two compounds?
They're the same.
Same molecule. Exactly the same. Any questions?
No, I just feel like the question's pretty vague when it comes to like
Yeah.
what's similar. Like honestly, I'd be confused if I saw it.
True, but when in doubt, always go to drawing it out and naming. That's the most easiest way you can tell
Yeah.
the relationship between two molecules. Always.
All
It
right.
may take some time, of course, but it's easy to do it this way than to try and look at it actually and figure it out just by looking at the projection. All right, next question. Question kind of faded, so we'll do it says, consider the following molecule with the molecular formula C4H8O2. So this compound. Which of the following constitutional isomers would you expect to be 1 trillion times more acidic than the compound shown above? So you can ignore the 1 trillion part. What the question is essentially asking you is, which of the following compounds down here is more acidic than the one on top? That's all this question is asking. So, one thing you must keep in mind when it comes to finding out the most acidic product, right, is strong acids will always make very stable conjugate bases, which is also a weak base. So when an acid gives up its proton, the conjugate base is very stabilized, right? So we have these 1, 2, 3, 4, 5 compounds. Let's draw the conjugate base for each of them. So we're going to give away a proton. In 1, let's give away the proton. Let's give away this proton. So the base will look like draw this hydrogen. All right.
So you're doing minus hydrogen to all of them? Like
No,
minus,
yeah, so let's say the acid already gave away its protons. Let's draw the conjugate base without the proton. In 2, I believe the hydrogen will come from the methyl over here. So if we draw the conjugate base, it's supposed to be oxygen here. And so you'll have a negative charge in that carbon there, right? Lone pairs on that carbon, negative charge. In 3, we can do the same thing. Hydrogen can come from this one. So let's draw that out. Carbon negative charge. All right. Or this proton from the oxygen be given. So if we draw the conjugate base, I'm gonna draw it kind of further down.
I remember doing this one with my friend, and because we saw that one, the 4 is carboxylic acid, we say, it might be that one.
That's
So we
smart.
didn't want to do it.
And 5, it could be any of the protons from these high oxygen. So let's do the one on top here. Draw the conjugate base. It's OH, and this is O, charge, and silicon. Oops, there's no oxygen. All right, so we have all the conjugate bases. So this is, again, 1, 2, 4, 5. Which of these conjugate bases is more stable? Remember, you want to take into account everything that can stabilize a molecule. So with acid and base reaction, we learned 4 types of stability. It's more electronegative atom. So the more electronegative, the more it can handle the negative charge. The inductive effect, which is if you have like dipole moments closer to where the proton is being donated. The inductive effect helps because it's also pulling electron energy away from the negatively charged oxygen, let's say in this case, the negatively charged oxygen, so that lowers the electron energy even more, so that's stabilizing it. Resonance is also an important factor. If you've made a conjugate base that could be stabilized through resonance, that's a good conjugate base. And snap, I always forget the inductive resonance, electronegativity. It's something else. Why do I always forget? I remember it, but yeah.
Okay, so the first rule you say
So,
the
which of these conjugate bases is more stable?
okay, so I think it's not 2, not 3. And I say 1, 2, I'm 4, 5.
Sorry, my headphones just unplugged, so I'm realizing it's so it was so quiet, but my headphones was unplugged.
So I'm
So
doing
you said 4?
no, I'm doing process of elimination. So I eliminate
Oh, okay.
2 and 3.
Mm-hmm.
But now I think I need to look at that thing. I don't know how to do that one.
Wait, can you go over what you've done for the problem so far?
So far, what I've done is you're trying to look
Yeah.
for the more acidic compound, right?
Okay.
When it comes to acidic compounds, after they give up their proton, the most acidic compound will always form a more stable conjugate base. This conjugate base is always stable. So what I've done was I've drawn the conjugate base of each of these molecules after they've given away a proton. In 2 and 3, the proton was given away from a carbon. That's why you see the lone pairs on the carbon that's negatively charged. And in 1, 4, and 5, the protons is given away from a hydrogen. So these are the conjugate bases we have here. Now, which one of these conjugate bases is the most stable?
Hmm.
I think it's 4. It can resonate.
Yeah, exactly. Resonance plays an important part in stability after an acid and base reaction. So for the carboxylic acid, it's a very stable conjugate base because of resonance. Electron pair can form a carbon-oxygen double bond there, and then this one breaks, electrons get pushed to this oxygen here. And it'll keep happening back and forth, back and forth, back and forth. It's the hybrid of the resonance. So resonance always stabilizes the electron energy even more. So because this can happen in 4, that means you form the very stable conjugate base. So since that's the most stable conjugate base, what can we say about the acidity of the original compound before the proton was donated? Is it more acidic or less acidic?
Less stable?
More.
More?
Remember, the most acidic compound will always form a more stable conjugate base. Since 4 has a very stable conjugate base, that means that 4 before the proton was donated is very acidic. Remember the definition of an acid. It's for a molecule that's willing to give away a proton. So the more willing it is to give away, that means it has to have a very stable product after that proton is gone. Otherwise, it wouldn't be so willing to throw away the proton anyways, because electrons and bonds keeps the molecule stable, remember. But if this acid is willing to break a bond from this hydrogen, that's because somehow, some way, the non-bonding electrons have to be stabilized. In this case, it's stabilized the resonance. Any questions?
No.
It's just a
Nah,
matter of remembering that acids will always form stable, weak conjugate bases. So as long as you draw the conjugate base and see if it's stable or not, then you'll have your most acidic compound.
okay. And you just remove the proton from every like conjugate base, essentially.
Yeah, from the acid. So when you want to figure out what your conjugate base will look like, just look at a proton, see, you'll be like, okay, let's remove this one. In most cases, it's always removed from the oxygen, but sometimes you won't have a hydrogen on the oxygen, so most likely it's removed from a methyl, a CH3. So you'll spot that
Okay.
out, draw the conjugate base, and then see which one's stable.
All right.
So let me paste this here because I drew it into like the next question. So the next question, 12. What is the IUPAC name of the following molecules? So we have a Newman projection, right? You have your first carbon, which is the one in the front here, and your second carbon, which is the big one in the back. So from the Newman projection here, we can actually number the longest carbon chain. We have a methyl on carbon 1 and a methyl on the back carbon, so that'll be carbon number 2. So you can say 2, 3, 4, 5. That's the longest carbon chain. Any questions on how I did that?
Can you draw like the
Oh, the
like-
sawhorse thing?
yeah.
Let me see if I can try with this one.
Okay.
Alright,
Yeah.
let's do the first carbon here. Second carbon there, and I'm gonna try and draw it out with that shape. So 1, 2. If you look at it, it's like a triangle. Oh. 4. So, there, that's better. First carbon has a CH3 hydrogen. Second, it's opposite. So CH3 and a hydrogen. Oh, that'll be your sawhorse looking. It's kind of weird looking, but you have your 5 carbons. Like I said, this is carbon 1, 2, 3, 4, 5. See it, right?
Yeah.
So this is your longest carbon chain. And of course you have substituents. So now let's get to naming the compound. You do have the methyls facing opposite directions in the Newman. So you do have to include something in the naming. What do you have to include?
Gotta include trans.
Right. Trans. Both those methyls are facing opposite. So when you see that in a Newman projection, you do have to include trans. So this is a trans molecule. Now you have a methyl on carbon number 1 and a methyl on carbon number 2. So what's the rest of the naming to be?
what is the name of this? It is trans 1,2
right,
and then dimethyl
right.
pentane.
So remember, we do see these carbons connected in a ring. Whenever you see this kind of continuing diamond shape, or sometimes, well, let me do this sometimes next, but whenever you see this continuing diamond shape, that means those carbons are connected in a ring. We did count 5 carbons connected in a ring. So, not dimethylpentane, but dimethyl what?
Cyclopentane.
Right, cyclo.
Okay.
So you have to watch out for that. Sometimes it'll be like this, or of course they can shorten the ring, or what you will see in some cases with the projection is this. Let's say I did this. There you go. So you have this too sometimes. This is the cyclohexane, the chair conformation, Newman projection. So you just need to look out sometimes what is in a cyclic ring and what's not. It's kind of hard to draw.
Wait, just could you repeat what's the drawing on the right that you made just now?
Oh, so this is the Newman projection for the chair conformation of the cyclohexane. So this was converted to this in Newman. So
okay.
this is how the chair conformation of it.
Yeah.
And of course, cyclopentane, the other chair, some chair conformations, when they're not flat, like going to butane and pentane, butane and up, they do have chair conformations too. The pentane, of course, will look a bit weird. It'll just be like this. Butane. I don't think there's a chair conformation. Butane. That's just like this. No, it is. It looks like a boomerang kind of. But yeah,
Yeah.
there's other chair conformations as well. But what we're learning about mostly is the cyclohexane chair conformation because it's stable.
Wait, Professor, can we go to number 11 again?
11? Sure.
Yeah.
Where's 11? Right here.
Number 2 can resonate too, right?
Which one?
You see the number 2? You have 2 lone pairs, so that can resonate too, right?
Oh, so 2 is this, where the lone pair is on the carbon.
Mhm.
This cannot resonate because there is no double bond here. So remember the pattern of resonance is if you have, let's say, a radical, a cation, a carbocation, or this negatively charged, it has to be next to double bonds. So what is next to right now is a single bond and an oxygen. It's not too close. Like say if it was closer to this, then you could resonate, but it's too far apart away from that double bond, so it cannot resonate.
Okay, now.
Okay. So it's just 4 that could resonate, right?
Right, only 4.
And that's why it's the answer, essentially.
Right.
All right.
Because the conjugate base is resonance stabilized.
Okay. No, because I was thinking about what you told me earlier about like more electronegative is more like acidity. Acidity.
Oh yes, that's true. You do have to take that into account when you're making your conjugate base too.
Yeah.
In this case, we do happen to come across a conjugate base that can resonate. So when you come across a resonance, that would be the most stable conjugate base, which means that that molecule that the proton was donated from would be more acidic.
Okay.
So the next question. Oh, look at this. 13. The following molecule, 2-bromo-3-chlorobutane, has been frozen in time, so there are no bond rotations happening right now. So it says draw 2 Newman projections that accurately represents this frozen conformation. So the first Newman projection would be seen from the left, and the second one seen from the right. So of course, the sideways glance of the molecule right now, this also will help us with the Newman projection because whatever is on the wedge and the dash is very important. So let's do the left one first. So the first carbon would be this one, and the big carbon would be represented by that one back there. So let's do the first carbon. We see a bromine pointing straight up is on a solid line. So we're going to draw it like that. Now, have this. The methyl is on a wedge, right? So that means it's coming towards us. So where do you think is going to be in the front carbon, on the right or on the left?
Left. On the left.
It's going to be here. It's going to be on the right. The reason is when you look sideways first, this methyl is coming towards us like this, right? So look at where the arrowheads go. It's going there. Now, if you were to look central down that carbon chain, that arrow is still going outwards like that. So it's going out to your right.
Mhm.
You see what I mean?
Yeah.
Yeah. That makes
So then
sense.
the hydrogen is on a dash. That means it's going away from us. So it's going like this way. And if you look at that from the eye point of view, that is what's going to be going off towards the left. Now let's draw our second carbon here. Chlorine in the back is on a solid line, so that's going straight down. It'll be like that. Now, what's going off to the left and what's going on to the right?
The hydrogen will go on the left. I mean the right, and
Mm-hmm.
methyl will go on the left.
Exactly. Your
Yep.
hydrogen's on the right. Your methyl is on the left. So this is our Newman projection seen from the left side of the sideways molecule. Any questions?
No.
Not at all.
All right. So now let's do the one from the right. Now this is going to be our first carbon. And this is going to be our big carbon in the back. So first carbon. The chlorine on the solid line is pointing down, so we have to draw a right side up wide out. Now what's going off to the left and what's going off to the right?
The left is the hydrogen and the right is the
Right.
methyl.
Exactly. Left is hydrogen, right is methyl. Big carbon. So bromine's going up, of course it's on the solid line.
Yep.
All right, so what's left and what's right?
The left is the methyl and the right is the hydrogen, the single one.
Exactly. Left is methyl. C3. Right, hydrogen. So this is our Newman projection from the right. You guys are good. No question.
No, not at all.
All right.
Wait,
So let's go.
can I ask them for the rest of the exams for the year, right? Like
Mhm.
other ones, are they all gonna be multiple choice or are they gonna be like a free response thing?
So for his exams, he really do mostly do multiple choice. If he have
Yeah.
short answers, it's like 3 or 4 short answer questions. At most 3, let's say.
Okay.
If he likes to throw some bonus questions sometimes, so he might throw in a bonus short answer question too.
Yeah.
But he rarely has short answers. He'll probably at most have 3 to 4.
Okay. Yeah, this exam's like really different.
Yeah.
From other ones.
Yeah, it is. The short answer. 14. Draw the Newman projection of and match the rotation around the carbon-3, carbon-2 bond in 2-methylbutane with correct position on the energy diagram. So, first things first, 2-methylbutane. 1, 2, 3, 4. Bam. 1, 2, 3, 4. They want Lubin projections down from the third carbon to the second. So that means your third carbon would be the first one,
Yep.
and the second carbon would be the big carbon in the back. So we're looking at it through this point, so down that central carbon-carbon. So before we start drawing the new ones, let's try and understand the diagram here first, this squiggly line and all.
Okay.
We learned about different conformations of Newman projections. You have the staggered, there's two types of staggered, anti and gauche, and then you have eclipse, two types of eclipses. All these conformations do have different energies. So let's look at number 1 right here. Number 1 is low, but higher than 3. So first off, what conformation would 1 be? Staggered or eclipse?
Staggered.
Right, it has to be staggered because it's lower in energy. Remember, the eclipse is always higher in it. So it's staggered. Now, we did learn staggered, anti, and gauche. Which one of those do you think takes up one?
Gouge.
Right, the gauche, because it's higher in energy than 3. The lowest energy staggered conformation would always be the anti. So 3 has to be the staggered anti. Now, of course, we didn't learn like, gauche or anti for the eclipse. So for the eclipse, we're just going to say low energy eclipse or high energy eclipse. 2 is which one? Which one of the eclipse?
High energy.
High and oops. The high energy eclipse take up 2. So then 4 is the low eclipse. Right. Now, let's draw each of the lumens respective to the energy type.
Wait, is there no gouge or anti
there is.
for eclipse?
One is gouge. No, so they don't do the gouge or the anti for the eclipse just because of how close together it is when you do the eclipse confirmation. So that's why he only says, okay, that's why we just come down to saying whether it's the high energy eclipse version confirmation or the low energy eclipse.
All right. Yeah. Okay.
So one we said was the gouge. So we're looking at down the 3, 4. Gouge. Methyl facing up from the first carbon. Then you have your 2 hydrogens. On the second carbon, we do have 2 methyls and a hydrogen. So if it's a Gauss conformation, where are the 2 methyls going to be?
Near the
Near
CH.
each other.
Right. They're the CH3 on the first carbon here, so they're going to be more upwards. CH3, CH3, hydrogen will be down here. This is the staggered Gauss conformation for 1. This is a new one. Right, so let's do 3. You said was staggered anti. So looking down the 3, 4 again. The first carbon will keep the same. So CH3 facing up with the 2 methyls down. Now the second carbon. If it's anti, what does that mean?
They're gonna be facing away from each other.
Right.
One-
One of the methyls is going to have to face the opposite from the one on the first carbon. So we're going to do that here. Then this hydrogen's here, and this methyl's going to go here. Even though one methyl is still closer to the other,
Mhm.
one is further apart. So there's less steric hindrance happening in 3 than in 1, which is why it's lower in energy.
Why do you do the left one that moves down instead of the right one for picture number 3?
Because it will be the same thing, just on, opposite sides. So let's say we do it like that.
Oh, it doesn't
It's
matter.
saying like, yeah, because you will still
Okay.
have a methyl near the one on the top. So
Oh yeah, yeah, yeah.
even if we do it like this, still the same.
Okay.
Both is possible though, so it really don't matter how you draw. It's good. All right, now let's move on to the eclipses. 2 is the high energy eclipse. So first carbon stays the same. That's all facing up. 2 hydrogens. Now, where are the 2 methyls on the back carbon go?
One near the CH3,
Right? So let's draw one here like that.
then the other one to the right.
Right.
There.
So here, and then you have your hydrogen. So this
Kinda
is the high
like,
energy.
it kind of like gouge. So because gouge
Yeah,
is
it is kind of like that.
Oh
It is.
yeah.
You can see it. You do see a resemblance with the eclipse and the staggers, but because of how close they are, we can't have the the vocabulary for the eclipse versions. We can't say like eclipse gouge and eclipse anti because all the groups are going to be so close together. So you truly cannot have the methyls facing opposite or anything like that. Unless it's in 120 degrees, which is what the staggered anti shows. So this is our high energy. And then we have our low energy eclipse. So what is that going to do? Let's draw the first carbon. And the lowest energy eclipse is going to be
one of the metal will be near the hydrogen
what? Right.
on the left.
The methyls will be farther from each other, not closer. So let's do
Yeah.
a hydrogen here, methyl here, and the methyl here. They're as far apart as they can be in the eclipse. None close together. So that's why this eclipse is lower in energy than 2. So
Okay.
there we have our Newmans respected to the diagram. Any questions?
No.
No, not really.
Let's move to the next question. We'll skip 15 because that's highlighted. 16. Carbocations are Lewis acids. They accept electrons readily. So, which of the following carbocations which you predict to be the most reactive? So, in other words, anytime you see most reactive, it's another way of saying least stable, always. So, what do we know about the stability of the carbocation? How are they stabilized?
By adding a protein.
So the carbon with the positive charge is more stable when you have other carbons attached to it. That's where the classifications primary, secondary, and tertiary come from. So a primary carbocation is least stable in a secondary one, which is least stable in a tertiary.
Okay.
Okay,
So
now I
this
can see now.
right. So now knowing this, which of these carbocations do we know is definitely the least stable?
2.
Yeah, number 2.
Right. This one here because it's a primary carbon. It's not, wait, no, it's not even primary. It's a carbon with a positive charge and all that's connected to it is hydrogen. No carbons at all. So this is very unstable for that positive charge, right?
Okay.
Now, let me ask you this. Suppose he say which of them is more stable. Which of these molecules, which of these carbocations here would be stable?
Okay, so tertiary will be the best for more stable. So
But what else do we see?
double bond.
Right. And what can happen with that carbocation and the double?
It can resonate.
Right. So anytime you go a step further into resonance always stabilizes very good.
Okay.
So then this species here is the most stable because of the resonance. So sometimes you see this little graph and then above that there'd be like resonance. Resonance is always most stable.
Okay.
Any questions?
No.
So you're saying that the fifth one just does resonance and
Mhm.
so that the fourth and the fifth are just tertiary, but you're saying the fifth one has resonance. So you get like,
So,
oh yeah, go on.
oh yeah. So the fourth one is tertiary and the fifth one is too. But since we can go an extra step and even resonate with the carbocation, that's stabilizing the molecule because it's being delocalized. Whenever you get a chance to delocalize energy around the molecule, that always stabilizes it.
Okay.
So 17. The following molecule is called glucose. So, which of the following chair conformations correctly represents glucose? What we're looking for is to put this molecule in the most stable chair conformation.
So equatorial, right?
Right. So we want to always push the biggest group that's on the biggest substituent that's on this molecule in an equatorial position. This case is going to be this group here. This is the biggest. So we want that in equatorial. Now we equatorial. So it's on a wedge, that means it's going up. So it's going to be equatorial up. What kind of carbon does it have to be on in order to fall in that position?
A down
Right.
carbon.
Opposites lead to equatorial positions. So since this group is going up, we want a down carbon to be equatorial. So this is going to be down. Then you just follow through with the other. This one will be up, down, down. Won't do it for the oxygen. It's just oxygen. Right. So we know we're pushing that equatorial. So now let's look at this OH on a wedge over here. It's on a dash, so that means it's going down. And it's on an up carbon. So what position will it fall?
Equal.
Right. Equatorial. It's going opposite. This OH down here is on a wedge, so that means it's going up. And it's on a down carbon. So what position?
Equal.
Right. Again. Equatorial. This one down here on a wedge, that wedge dash, so down. It's on an up carbon, so what position?
Is
Equal.
equatorial.
Right. And this last OH on the wedge is going up because it's coming towards us and it's on a down carbon. So that means what?
Is equatorial.
Right.
Okay.
So in the most stable chair configuration, all of these substituents here will be in an equatorial position. So which of these chair conformations bestly represents this? What we came up.
It's not the third one.
Nope. Definitely that one, because we do see an axial OH, which is wrong. What else can be eliminated automatically?
3, 4.
Right. You see an extra OH here. We're only supposed to have what? 1, 2, 3, 4, 5. We're only supposed to have 5, and this one we have 6. So that is out of the question. So we're between 1 and 2. Which one represents what we draw?
Uh, isn't it 2?
It's
Yeah,
two.
yeah.
All of them are equatorial. If we look at one, we do see an OH here and an axial, which is wrong.
Yeah.
None of them is supposed to be axial. So the only chair confirmation that matches what we did is 2.
Yeah. And then just to make sure, you said the wedge is up usually and the down is the dash.
Right. Wedge means it's coming towards you, so it's up, and then the dash means it's going away from you, so it's down.
Okay.
Move on to 18. Which of the following molecules would have the lowest heat of combustion? So when we say lowest heat of combustion, what's another way of saying that? It would be what?
Wait, just a question about the last thing that we did, right? You said equatorial is higher in energy than axial, right? Or something like
Oh
that.
no, equatorial is lower. So you always want to push the groups in the equatorial position, which is lower, because it's not gonna line up with any axial groups. So that causes less steric hindrance.
Okay. All right. And then with combustion,
So lowest heat of combustion. In other words, the molecule is what?
molecule
What does that say about their stability?
stability. Um, huh. Um,
More stable.
More stable. Another key for that is anytime you see the lowest, always think of lower in energy. So lowest relates to that, which means you look for the more stable. So which one will release the least heat, which is stable. So you have all these molecules listed here. Let's draw each of them out. So let's draw. So one is trans 1,2-dimethyl. So that's cyclopropane is 3 carbon. I'm the ring here, which is triangle. This is trans. So let's put 2-methylcyclopropane. So that's just your square. 3 is cis 1,2-dimethylcyclopropane. So it's exactly like 1, except now both is on the same. So let's do 4 cyclopentane. That's your pentane. And 5 is your cyclohexane. So now, which is more stable? Which answer choice do we know we can automatically eliminate?
Mm, 2.
What up?
uh,
So
let's-
you definitely know you can eliminate 3 because both those methyl groups are going in the same way. That molecule is definitely not stable because of steric hindrance. And remember, some of these cyclic rings, they suffer from steric hindrance too, which is not steric hindrance, torsional strain, which is another way of saying angle strain. Because of how small the angles are, that's causing a lot of strain with the carbons attached to that ring as well. So cyclopropane, that definitely has a lot of angle strain, so you can eliminate 1 as well, even if those methyls are trans. Because of torsional strain, that's also going to make it unstable. So between 4 and 5, the cyclopentane and the cyclohexane, which one is more stable?
The hexane. 5.
You say the hexane, but the actual answer is cyclopentane. The reason is because when it comes to the cyclic structures,
Mhm.
the more, by definition, cyclohexane is more unstable because the more carbons you have in the rings, the more heat of combustion you will have too, because of the amount of carbons you have. So cyclopentane, that's one less carbon than cyclohexane. So that's why cyclopentane is more stable. And this is due to the fact that when you do the reaction for the heat of combustion, you're reacting these with O2. So when this reaction comes into play, what you create is a lot of CO2. So the more carbons you have, the more CO2 you create, which is a very combustible reaction. Questions?
Okay. No. I know he said it in like the PowerPoint that there was something with cyclopentane and combustion.
Yeah. So that's when it comes to the ring structure. So like the skeletal structures too, same thing, more carbons, the more possible. But in the ring, cyclopentane is stable.
So if they
It
would
has
ask,
least torsional strain. It barely has torsional strain, I mean, and it don't have too many carbons.
okay. So if they would ask me for the highest heat of combustion, it would be 5.
So highest heat of combustion, yeah, it would be 5.
Okay.
Yeah. So let's look in the T. What are what are the most likely products of the heterolytic cleavage of 2-chloro-2-methyl? So you do know what a heterolytic cleavage is, right? So let's say you have HCl. When it's cleaved this way, that means both of the electrons from in the bonds goes towards one molecule.
Okay.
Homolytic, which is another type of cleavage, that's when it's being equally shared. So that's when you see this. You always see, and instead of a full arrowhead, it will be half, which represents one electron. So one will go back to H, and one will go back to chlorine. So this is homolytic. Never mix up the two.
Okay.
Heterolytic, both electrons. Homolytic, one goes back to each. So, which type of heterolytic is likely to happen in these bond breaks? So 1, 2. So when that happens, we do end up with a negatively charged atom. So which one do you know can definitely handle negative charge better?
Okay, it's not 4, but chlorine can. So it would be number 2.
Exactly. This will most likely be the cleavage. Because the negative charge is going towards chlorine, which it can handle because chlorine now it's a bigger atom. So the
Yeah.
halogens, because of their size, they can handle the negative charge as well because the electron energy is being spread towards a bigger surface. And then positive charge on the carbon, which is most likely because carbon is less electronegative. Any questions?
So it heterolytic cleavage, it just goes the bigger one, like the electrons, or
So yeah, so heterolytic, you would know that because chlorine is a bigger atom, it'll handle the negative charge. So both electrons will move to the chlorine, not the hydrogen.
yeah. And then homolytic's just both. It's like split
Right.
up. Okay.
Homolytic
makes-
is both. So when it leaves, this hydrogen have one electron, and the chlorine would have about 7. This.
Okay.
and hetero to the charge, and all electrons to give.
All right.
So it's funny. Huh? Come across a question like this again. So the most stable conformation of a compound X has what? So each of these substituents, we know the top one here, this is an ethyl substituent. This one here, the CCH33, what type of substituent is that?
What type of substituent? Oh, someone left. All right. What type of substituent is this? It's
Yeah.
the. What is this? It's like it's a bunch of methyls, right?
Right. So 3 methyls attached to 1 carbon. Like this. What is this group called?
What is it called? Um.
Remember, it's tert-butyl. So this is a tert-butyl. Whenever it
Oh,
looks like this chicken foot, does it do like
yeah.
a chicken foot? It's a tert-butyl.
Okay.
There's another substituent that kind of looks like that, but it's not the same. That's this. And this is isopropyl. So I like to identify this as snowman always. That helps me, like, tell the difference between the two. And I can name it. So this is a tert-butyl group. And then down here, we're working. So in order to have the most stable chair conformation, we always have to push the biggest group in an equatorial position. So which of these substituents is big? Is the biggest one?
The third butte.
Yeah.
Right, exactly, the tert-butyl. So we want that in equatorial. It's on a wedge, so that means it's going up. It's going to be equatorial up. So then what kind of carbon does it have to be on?
Down carbon.
Down.
Right. So then this is up, down, up, down, up. Now let's look at what the other two substituent positions are. Let's look at the ethyl. It's on a dash, so that means it's going down. And it's on a down carbon. So what position will it fall?
Gonna be axial.
Axial. For the methyl. It's on a dash, so that means it's going down. It's on an up carbon.
So it's equatorial.
So, which of these answer choices best match what we got for the chair conformation in the skeletal structure?
It's gonna be A.
So the most stable conformation of compound X have an equatorial methyl group and an axial ethyl. And
Okay. Yeah. You explained it perfectly.
all right, so next question. Question 21, skip because you don't know Dill's powder reaction yet. 22 is locked out. I think he won't put a question like that on the exam. So let's go to 20. 1,3-dimethyl cyclohexane can exist in 2 stereoisomers, cis and trans. So describe the relative stabilities of the isomers. Although this question don't seem like it, what he's asking you about is the chair conformation of the stereoisomers. So we have to draw the chair conformation of each, the cis and the trans. So let's do the cis. First chair conformation. So on carbon 1 and carbon 3, we have methyl. So this is cis. Both facing up, right? So they're both going to be on an axis.
Okay.
Now, remember that these chair conformations always go through ring flips. So let's ring flip this first cis conformation. So all down carbons become up, all up carbons become down, and that means all axial substituents become what?
Equatorial.
Right, that always happens in a rainfall. So these two that was on axial become equatorial, like this, 1 and 3. So this is for cis. Now, let's do trans. So one, let's do it's like this, right? So now let's do the ring. Alright. So then this becomes axial. This becomes equatorial. Alright, so you have all these chair conformations of both the cis and the trans, right? Now,
Yeah.
which one of these is more stable?
Cis, the second one with the withdrawal.
Exactly. Why? Why is this more stable?
Because it's more equatorial.
Right.
For the
Both
methyl.
the methyl groups are equatorial.
Mhm.
So whenever we have any of the other substituents in an equatorial position, it's automatically going to be stable. So this means that the cis is stable than trans.
How do you know that for the first cis one, all the way at the left, the figure?
Mhm.
How do you know that they were both axial, like the two things that you drew?
Oh, because both substituents are going to be facing the same way. So in order for them to face the same way, they have to have the same type of position in the chair conformation. So either both cis or both, not both cis, either both up axial or both up equatorial. That's how it is for the cis conformations all the time. So you just draw methyls on carbon 1 and 3, and you could just draw them both axial first, then do the ring flip. Or if you could have done it vice versa too, you could have drawn them both equatorial up, and then after you do the ring flip, they would have been up axial as well.
Oh. Okay. Yeah, we go to the next one.
So question 24. Rank the following in order of decreasing importance as contributing structures to the resonance hybrid of formaldehyde, H2CO. So this is formaldehyde. So we're ranking them decrease in importance. So we're going from most to the least. So we have 1, 2, and 3. Which
Oh.
one can we say is the most important?
Oh, this is on the first exam.
Yeah.
Mhm.
Oh my gosh.
Okay, so carbon doesn't want to be positive. So I would say 2 is the most.
Right, 2 is the most. The reason why it's the most is because when you're doing like resonance contributors, the
Yeah.
original before you start the movement will always be the most important because it's from that we would figure out, okay, what can go to what. That's why 2 is the most. So then, out of these two, which one is the least?
Which one is the least?
Yeah, which one's the least important? So we do have charges formed after movement, right? We have a carbocation and a carbanion. That's the negative charge, another way of saying that. So
oxygen.
next,
Okay, so oxygen doesn't want to be positive. So I would say 1.
negative. Remember, oxygen is more electronegative, so they better handle the negative charge than the positive. The positive charge, we always want it to fall in the least electronegative part. So the least important one here would be 3,
Maybe the right one. Okay.
right? Because you have a negative charge on the carbon and then you have a positive charge on the oxygen, which is very weird for us. It's like, nah, it should be the other way around. And then 1 is, we just say it falls in the middle. So then it goes 2, then it's 1, then it's 3.
Okay. What was the like the background reason to say why oxygen can handle the negative charge better than the
Oh,
carbon?
because it's more electronegative. So remember, more electronegative atoms, they always handle the negative charge better.
Oh, that's what it means. Okay. Yeah. All right.
Move on to 25. What is the IUPAC name of the following Newman projection? So again, let's do the sawhorse joint so we could name it better. So carbon in the front, carbon. On the front carbon, we have an isopropyl, chlorine, and the methyl, just like that. And in the big carbon in the back, we have a chlorine this way, hydrogen this way, and an ethyl group. So boom, boom, just like that. Now, first thing we have to do when naming is what?
Find the longest carbon chain.
Longest carbon chain. So how many carbons make up that long chain?
5.
Mr. Warren.
6.
Right.
Whoa. Oh, dang.
Remember, anytime you can try and like push carbons from existing substituents into the long carbon chain, you should do that. So
Yeah.
like one of the carbons from the isopropyl will definitely fall into the longest chain. So 1, 2, 3, 4, 5, 6. This will be
Okay.
a longest carbon chain.
Yeah, I was
Then
looking
you
at the
have
bottom one.
methyl substituent, chlorine substituent, methyl substituent, and a substituent here. So now let's get to the numbering. Where will we start numbering?
Top.
Top
Yeah.
left, because we come to our across our first substituent there. So 1, 2, 3, 4, 5, 6. All right, we numbered, found our substituents along the carbon chain. Now the last thing to do is name. And remember, name in alphabetical order. The prefixes don't fall into the alphabetical. The substituent do. So even though you have like dimethyl, let's say you have dimethyl and diethyl, the ethyl will always come before the methyl. You ignore the prefixes and pay attention to the group. So let's get to naming. What will we name first?
3 to 4 dichloro.
Right, exactly. Begins with a C, so it comes first. 3, 4 dichloro. All right, what's next?
Wait, let me see. Esto.
It's like
I
2.
met.
Yeah, so we do have this substituent here, methyl, and another methyl substituent here. So 1 on carbon 2, 1 on carbon.
Dang, I forgot the numbers.
Yeah, so it's 2, 3, and then
2, 3,
dimethyl
and longest carbon chain,
is heptane, dimethyl heptane.
hexane.
Hexane.
Heptane
Okay,
is
I
7.
got you. Okay.
So there we go. The name of this molecule is 3,4 dichloro 2,3 dimethylhexane.
And a quick question, right? You said isopropyl or something like that earlier. Could you explain
Oh,
what
yeah.
that is?
So what I said was like before we included the longest carbon chain, right? You
Yeah.
have this substituent on your first carbon. Whenever you see this is called an isopropyl.
Propyl meaning 3, and then iso is just
Yeah, I guess it's the way it's because of how it's shaped. That's where the iso comes from.
okay.
You know, scientists came up with these names way before we started learning them. So why they have
Yeah.
certain IUPAC names is still kind of I'm still trying to figure that out in some cases.
All right.
All right, let's go to the next question. Rank the following conformations in order of increase in energy. 1 as the lowest energy and 4 as the highest. So we do see different conformations. We see 2 staggered and 2 eclipses. So now it's about the energies. So between the 2 staggered here, let's say, let me do it this way. So
1.
2, 4 is like this. Yeah, that's 4.
Is
So-
it for IV? Is that
Oh,
that
it's
safe?
Ivy? Oh,
Yeah,
I'm
I don't want to be
sorry.
that guy. That's all
well,
good.
no, I want to learn. But these Roman numbers is kind of hard to me.
Mm-hmm.
I always mix up the 4 and the 6. Always. All right. So between the 2 staggered conformations, which is 1 and 4, which one is lowest in energy?
1.
Right, 1.
Yeah.
2 methyl groups are close to each other, only 2. And then you do have a methyl that is anti to one of them. So this is the lowest energy combination. 3 has all of these methyls put together. So that's a lot of steric energies. So we can rank 4 as 2. Because the staggered is still the low energy conformation. Now, 2 and 3 are the eclipse conformations. Which one is lower in energy than the other?
2 is lower.
Right. All those methyls are further apart than in 3. So then 2 gets ranked 3, and that means 3 is ranked 4. It's the highest energy.
I just look for eclipse anti, basically.
Yeah, you can say that equals anti.
Yeah, I might start doing that.
Yeah, it's easier.
Yeah,
It is, honestly. Which is why I don't know it's not like not in the vocabulary. Even though it's close together, we still do see a relationship between the antis and the dots. So I would think like that. All right, we have time for one more, I think, 27. The following molecules react with HCl+, so that's hydronium, and an acid-base reaction. Which of them is the least reactive? So we're looking for which of these molecules is the least reactive. Now, what do you think we have to pay attention to?
yeah. Probably electronegativity and then resonance, something like
Exactly.
that.
Those are the 2 you would, because we do see double bonds, and we do have, oxygen and nitrogen is 2 atoms we're looking at. So we're going to look at electronegativity, and want to look at what can we see. So these 3 atoms. Which one of these choices can we automatically eliminate? Let me say 1, 2, 3, and 4. Which one do you know isn't least reactive?
2. Because it can't resonate. Well,
2 can't resonate, right? What else can we eliminate?
And you eliminate 3 because you can't resonate
Right.
that also.
You can't resonate, and we're working with nitrogen. That's the least electronegative, so it is very reactive. For this question, we're looking for the least reactive. So 3 is out of the question. Now we're between 1 and 4. Between these 2, which one is the least reactive? They both can resonate, yes.
1.
Right. O is more electronegative than nitrogen. So those electrons in oxygen isn't so reactive right now. And we could take it a step further and say it's very non-reactive because it can resonate. Oop, wrong way. So we create a carbon oxygen double bond and just move it down here. So the resonance is also keeping it very stable. The answer is 1.
Mm,
Any questions?
no.
So I think we do have time. Question, and this one is a good one. So 28, identify species that results from the following movement of electron pairs. So we did at one point learn about arrows and what. So this first movement here, from the electrons on oxygen to hydrogen, what's good? What does that mean?
Okay, so that double bond, that lone pair on the oxygen, get the hydrogen, and that hydrogen bond
So lone
get the
pair
double bond.
snatch hydrogen. And the hydrogen bond, what?
Uh, the hydrogen thing, yeah, bond went to the carbon bond and became a
Right.
double
So
bond now.
the electrons in this CH bond,
Mhm.
it so the elect oh, just found- so the electrons go to carbon carbon. So that creates what kind of bond?
A double bond between the.
Right. So then a double bond is
Um,
created. And the last arrow means what?
Oh, that double bond went to the oxygen, so we
Right.
have two more
So
here.
double bond will break
Mhm.
and the electrons is pushed onto the oxygen. So in the end, which of the following shows the correct movement that these arrows are identified?
Also, that was the question asking. Okay, so
1, 2, 3.
it's yeah,
look like 3.
yeah,
Yeah,
three
Right.
was my first
It's
thing.
definitely correct. So first we identify what each of the arrow movements mean. This OH minus, the hydroxide, takes the proton away from that carbon. Whenever that happens, you always form water. So you can automatically eliminate 1 and 4 because we have no water. After that, it's still, remember, all of this is happening heterolytic. So heterolytic. Once the water, the OH snatches away the hydrogen, the electrons from the CH have to go somewhere. So they go to the carbon-carbon bonds, creating a double bond. So we do see double bond created in. And lastly, that last arrow means that the other double bond has to break and the electrons get pushed into oxygen. So that's why 2 is out of the question. Look at this. It's violating the very bad
Yeah.
right now. So
Okay.
the answer choice is
And then, oh wait, one question, right?
Mhm.
Lone pair snatch H, that first arrow. Essentially, you're
Mhm.
saying the H shell with the lone pairs on it, they like took that bottom hydrogen that it's
Yeah.
pointing at and they put in its own thing.
Right. So the O is just like, all right, you come here, we're gonna form water. Let's let you leave C and join me.
Why did it leave the bond then? It made its own separate thing. Like
So that it can become more stable.
I thought the HL would go to the H, to that single H, and I thought they'd combine with the bond.
Oh no. So they wouldn't go in and join in. It wouldn't happen like that. Never in that case would it happen.
Okay.
So whenever you see electrons go into a proton, that means it's just taking it away for itself. It wouldn't like make a bond and then join in with the rest of the molecule. It never happens like that.
Yeah. Okay.
Okay.
All right.
So
Uh,
once